And these are some commands to just rename this xy in the proper form, like z tandem, v tandem, like that. So if you, I think these commands are self-explanatory, like set skip variable, x name, z tandem, y name, v tandem, like that. You can go through this command. If you do not understand, we can come back. And then comes the visualizing the IV. So this plot, draw, ZU, VW. So we are plotting those three IVs separately. And finally, we are calculating the overall VOC, JSC, fill factor, and the eta of the tandem cell. So this script variable, and so script variable shows this outputs the variable after a simulation. So if we simulate this, so we will go and click execute script. So now the top cell is being simulated. Now the bottom cell is being simulated, and these are the overall results. If you can see this V top. Actually, these are not arranged in order. So these are voltage of the top cell, and this is the current density of the bottom cell, the first and the last. For some reason, it is like rearranged. And the second and the third column is the current density and the voltage of the bottom cell, and fourth and the fifth are the current density and the voltage of the tandem cell. So if you see these values, so this U is the efficiency of the tandem cell, which is like 31%. So earlier we while simulating the individual cell, if I remember correctly, so for PN junction we are getting 21%, and for perovskite also we are getting something around 20 only. But when we combine them, we are getting this value of like 31% efficiency. So similarly, this X is the VOC, Y is the JSC, and this Z is the fill factor. So if we click continue, we are able to see this is the IV of the top cell, and if we click here, this is the IV of the bottom cell, and this is the IV of the tandem cell. So if we plot them together, we need to select all three and click refresh, and you will get the three IVs together. If you can see here, that's this green one is the IV for the tandem cell. Then the JSC current is equivalent to this red plot. So that means the tandem cell current is the current is equal to the minimum of the two JSC values. So which is matching it, and the VOC value is the summation of these two voltages. Okay, but here what we have done, we have just mathematically connected these two subcells and calculated their this solar cell parameters. But when this is actually a very ideal case, but when we comes to a real tandem cell, there are like many factors which reduce their performance. So maybe one is when we shine the light. So if we go here, when we shine the light from the top side, so the some part of the light is being absorbed, and only a certain part of the light is reached to the bottom cell. However, in our simulation, we have considered both the top and the bottom cell are getting same 1.5 intensity, 1.5G AM 1.5G intensity. So this is not correct. So and similarly, so all the generated current is not being collected at the output in case of a tandem cell. But however, while simulating these two cells separately, we have considered that whatever is being generated, we are able to extract it fully. So for that, to consider all those these factors, we need to go for a second strategy. So in this strategy, actually, first we need to design the entire tandem cell, like in the script, not in the SCAPS set problem menu. So here, if we go to the set problem, in this method, you have to design the entire tandem cell here, like with all the parameters. So for example, if I want to show you, like this. So this is the structure where all the layers are there. All the layers are present, and just to check, if we run it as it is from here, so basically why we have opted to go for a script, like rather than simulating it here. If we run it like this here, you will see. So there is convergence failure even at the first step, because there are many layers and the many. So the simulator is not able to converge even in the first step itself. Therefore, we have to go to the script method to simulate this tandem structure. So in the second strategy, we have to design this entire structure first. Then using the script, we need to we need to load this entire tandem cell in the script. Then we need to split it into top cell and the bottom cell separately, and then these things the script automatically splits it by using some commands, and do the simulations part by part and completes this tandem cell simulation. But I don't think we'll be able to cover this part, because this needs some more time to cover all these points. But just to say, these are the commands that you need to do this splitting in the script file itself. So if we write this tandem splits, this split generation stays tandem split generation.script. So it will split the tandem cell into two parts, and it will consider generation separately for the two cells. And if we go for this adapt filter varying RB, so it considers the reflection at the interfaces of the two cells, which we have not considered in the previous strategy. And in the third case, tandem test, test tandem split fake top and bottom script. Here, they split the two cells, and while simulating the top cell, they consider the bottom cell is electrically inactive. It is only present, and they contribute to the optical simulations only. So it is more realistic than the strategy one that we have seen here. So, and while simulating the bottom cell, the top cell is considered electrically inactive. So the details of this method can be found in the manual. However, for this demonstration, actually, we'll be not able to cover it, because this needs some more knowledge of some more these commands. And coming back to this thing. So at the end, we want to show a simulation, show a tandem cell simulation using the first strategy only, from a research paper from our group, which is a FASNI3 and CSFAPBI3 based tandem solar cell. So here, if you see, they have optimized this thickness, and they have achieved an efficiency of 11. And here, if we try to, so we'll just show like we have already created the two subcells. This is the first top cell, which is based on FASN3. Yeah, this is FASNI3. No, I think the name is not correct, actually. This should be CS FAPB X3, because this is a wide band gap. If you see this thing, this CS FAPB X3 is the wider band gap. So I'm just skipping it. So this is the first subcell, and if you load the second one, this is the second subcell. and it has a band gap of 1.4, and the previous one has a band gap of 1.8. So we have already simulated these two individually, so it was running. So if we run this same script file for these two, just a second, let me confirm the name once again. CSFU. I'm just changing the name of the two definitions file, and the remaining things are same. So other one is the FASN open cell. I think it should work. So I'm just writing execute script. Yeah, so this is the results for the tandem cell. So if you see, this is U value is the efficiency, which is near 11.9. And if you go back to this paper from where we have taken these two examples, they have also achieved a efficiency of 11 when they use this thickness 200, the thickness of this active layer 200. So we have also used the thickness of the active layer 200 only. And these are the 3 IVs of from this paper. So it is not coming properly. So if you want to see properly, you need to go to scale, manual, and give whatever value you want to see here. Yeah. So this is the IV from this example. Yeah. So I think we have shown the simulation of this tandem cell. So we have planned to show some CV simulation also, but I'm not sure whether we have time or not. So, hello.
Yeah, Dr. Himanshu, the time is up. We don't have. Can take 5 minutes.
Okay, so either we can show the CV, or we can take the questions in the chat box. There's like some questions in the chat box.
Yes, we have so many questions. After that, one main question is, what are the reasons for getting this convergent error? Some participants have asked that they have got convergence errors.
Yeah. So convergence error. So convergence error is that like the because of the numerical settings that we are using. So the simulator is so it is doing the calculation using some numerical method. So whatever parameters we are giving, so it is not able to. So that numerical calculation have to converge to some solution. So it is not able to come. So that is why whenever we are doing simulation, you see we are using this stop after VOC, because after VOC the currents increases very rapidly. So it is uh, to get rid of this convergence error, you have to optimize your this simulation parameters as well as this simulation settings. So for that you have to spend some time and get the meaning of all these parameters, and you can also go to the manual and understand what is the meaning of all the parameters.
So the next question is how to load new data or material which is not available in the software.
Yeah, we have already shown in the in this workshop how to add a new material, which while defining new structure and then clicking on the add new layer, there you will get the window where you can input all the material parameters and save it. That's how you add a new material.
Thank you. Next question is, how to know the correctness of the results for validate simulation?
Can you, sorry?
How to know the correctness of the results or validate the simulation, the results, the plots?
Yeah, correctness. To get the exact correctness, we have to fabricate the device and get it compared with the simulation results. Otherwise, accuracy.
Okay, we'll take one more question. So, can we include the plasmonics property too of the material in SCAPs and study device properties, specifically semiconductor infrared plasmonics, like we observed in dope metal oxides?
Well, in SCAPs, you can simulate, you can add any layer which you can model as a crystalline band, model as having a crystalline band structure. If you can assume that, then you can simulate it. I'm not sure whether plasmonics can be modeled as crystalline models as having crystalline band structure.
Okay. We have a few more questions, but we request you to address them in the chat box. Now, thank you, Dr. Himanshu Gogoi and Mr. Abdul Basit,
Thank
for
you.
the session. Now, thanks to all the participants and speakers for making this morning session on solar photovoltaics exciting and successful. Now, we will break for lunch. Participants are requested to be back online by 2:10 p.m. for the afternoon session, where we will have technical talk at the tutorial session. Thank you.